Hi everyone, in this video I'm going to go over section 4.1, which is about maximum and minimum values. The beginning part of this will mostly be prereq stuff, so I would say from pre-calc 1 really, and then I'll put a couple of new things in terminology wise, but the beginning we'll just review prereq stuff and then we'll get into the calculus part of it. This is going to get more complex when we go to section 4.3, but for now we're going to be on a closed interval. And remember, closed intervals are ones with brackets, so like a specified interval that's not going to keep going and going. When we get to open intervals is when this gets a little bit more complicated. So the main intent for section 4.1 and 4.3 is to allow us to do what we call maximize and minimize values. So when we look at these, we're going to look at maximum and minimum values. That's the title of the section. But we're going to see in section 4.7, which is at the very end of the course, it's another tough one, kind of like 3.9, that what we call optimization is really important in mathematics and really in other fields. So if you have a function that models something and you can figure out how to, say, maximize it, then maybe if you're in business, you could maximize your profit. Or if you're creating some engineering system or you're creating something using engineering, you can figure out when it'll be at its max performance. Or if you're working for a packaging company and you want to make the smallest package, so fit what you need in the smallest package, then what you can do is minimize that package. So there's a lot of motivation application wise. I think that you'll like section 4.1 because I think it'll feel a little bit more gentle than, say, section 3.9. So it's going to be pretty mechanical, although we should understand like the prereq reasoning and the basic reasoning behind it. So let's go ahead and get started. All right, so first few things that we need to recall are what the local maximum, local minimum, absolute maximum, and absolute minimum are. So remember, the local maximum is going to be the y value. I'll type this in. The y value of the point. And this should say when the function goes from. So when the function goes from increasing to decreasing. So y value of the point when the function goes from increasing to decreasing. So we can see here we go up, it's increasing, we go down, it's decreasing. You can see that that would be, this little red dot would be the maximum value of this part. What we could say in layman's terms is we're looking for the little mountains or peaks of our function. So mountains or peaks. Okay, local minimum is the y value of the point from when we're going to, you could probably guess, decreasing to increasing. So from decreasing to increasing. Okay, and just like the local maximum, there could be multiple of these. If we want to put this in layman's terms. Okay, what we're looking at are what I call the little valleys in the graph. So think your hills or your mountains or your peaks are going to be your local maximums, and all your little valleys are going to be your local minimums. Okay, so the absolute maximum, sometimes called the extreme maximum or the global maximum, is the largest y value in the function. So the largest y value in the function or in the domain. So remember, the domain is just, what range of x values you're looking at. The absolute minimum is going to be the smallest y value in that domain or in the function. Okay, so hopefully you remember that at least a little bit from pre-calc. If not, we'll go over a couple things, so it should be okay, and then we'll jump into the calc part. All right, so first thing we want to know is if f is continuous and if the domain is a closed interval. So remember what I said earlier, the closed interval is when you have brackets, so the endpoints are included. That means you have this specified interval where your endpoints are included, right? Then you're also going to have to check the endpoints. So some people will make the mistake of thinking, oh yeah, I'll just check this little spot and this little spot and this little spot. But think about it, your endpoints could also be max and min. So for example, in this little chart, you can see that a and f of a, this point right here, that is the lowest y value on your point. So that is that is the absolute minimum. So when we go through these, we need to check all these little valleys and all these little peaks, because maybe instead of being local max and mins, they're absolute max and mins. But we can't forget to check the endpoints, because you can see in this example, sometimes those endpoints can fall below the lowest points, or perhaps if this was extended up here, it would fall above the max. So we're thinking, all right, we're going to check these hills and valleys, and we're going to check our endpoints when we have a closed interval, meaning when the endpoints are included. Okay, so how do we do this? Well, we can use calculus. So if you look in this little pink curve or this first curve, you should recognize like, oh, wait a second, at this little hill, I know my tangent line is horizontal and my derivative is 0. Okay, I know at this little hill, my derivative is 0. I know at this valley, my derivative is 0. And here I have a sharp turn, so I know that my derivative is undefined, because remember, when derivatives are undefined, when we have sharp turns, that's one place where a derivative can be undefined. Okay, so to put specific language or verbiage to this, these little spots that I just discussed are called critical numbers. So a critical number of f of x is at x equals c, or you could have any letter instead of c, in the domain where the derivative is 0 or the derivative does not exist. All right, the second line of this is really just an implication. So if f has a local max or min at x equals c, and if f prime exists, then we know the derivative is 0. So if it doesn't exist, we have a sharp turn. It means the derivative is undefined. If it does actually exist, then we know the derivative has to be 0, because if you think about in here, okay, when we have these turns, the derivatives are all 0 except for when we have that sharp turn. So the only time the derivative couldn't exist and that we could still have a local max and min is when we have that sharp turn. All right, and this I think will make even more sense, hopefully, when we get to the computational part of this. All right, so let's look at this graph. And what I would do if I were you actually is pause yourself and look at each point on here and go through yourself and label it. Okay, is my derivative 0 or does it not exist? And then ask yourself, is this a local max and min? Is an absolute max and min? So I would pause this and try it yourself, but I'm going to go through it as well. Okay, so I'm going to look at each point on this graph. I guess blue is fine. All right, first I'm going to go through and look to see where the derivative is 0, where it's undefined. So here, I know at this little spot, f prime of x is in fact 0 because I have a flat tangent line. Okay, here, the derivative is also 0 for the same reason. Right here, the derivative is undefined. That's because I have a sharp turn. Here, the derivative is undefined, again, because I have a sharp turn. And then at the end points, the derivative is not undefined or 0, so we just don't have to put anything there. Okay, so now I'm going to look for absolute max and mins and local max and mins. All right, so I see in this spot right here, I have a valley. So I know that this is going to be a local minimum, and that's because I see part of this extends down further. So this is a local minimum. All right, coming up here, I have a little peak here, a little bitty peak, but I see this tall mountain over here. It's definitely higher, this spot's higher, so I know this is a local max, and there's no way it's an absolute max. All right, coming up here, this looks like, we're gonna pretend like these two are the same height. So what happens when you have the same height? You actually get two absolute maximums. So this is an absolute max, and this is an absolute max, and that's because they have the same y value. So really, that y value is the same. So let's say the y value were 4, then we say, okay, our absolute maximum is 4, and this happens at the x value of whatever the first one is and whatever the second one is. All right, and then finally, this one's real clear. We can see down here, this is definitely the lowest point on our function. So this is going to be the absolute, or you could say the global minimum. All right, so hopefully you were able to kind of roll through that on your own. If not, hopefully what I said made some sense, and I think we should try more. All right, I tried to make these a little bit different. So let's on this one just focus on finding I'll write this out, local max and mins and the absolute max and mins. So let's just identify those for now. Okay, so if I'm looking for local max and mins, then let's start with local minimums. So let's see, right here. Okay, so I wish I would have made this bigger. Okay, so this behaves a little weird, which is part of the reason we did this, but if we look at local mins, all right, so we see right here, and I will erase this in a minute,